This lesson is part 2 of section 10.8 on DeMoivre's theorem. I know that in yesterday's lesson we never actually got to DeMoivre's theorem, so today we're going to introduce you to what DeMoivre's theorem is, and then we're going to use it when we do binomial expansions that involve complex numbers. So rather than relying on Pascal's triangle, we use DeMoivre's theorem. We are also going to use DeMoivre's theorem to find the nth roots of complex numbers. So DeMoivre's theorem gives us a very nice formula to use when we want to multiply repeatedly some complex number. So he was able to see and also prove a pattern that we're going to be able to see here as well when we try to multiply a complex number by itself. So I'm going to first start with finding z squared. Now z is defined as r times the cosine of theta plus I times the sine of theta, and I'm not going to make this shorthand into cis form. I'm just going to keep it in this form here. Alright, now if I want to find z squared, that means that I want to find z times z. And if I'm multiplying z by itself, I need to make sure I multiply the moduli by itself. So I have r times r, or r squared. I also have to make sure that I add the arguments. And if I add the arguments, each argument is theta. So I have cosine of theta plus I times the sine of theta plus theta. Now if I simplify, I end up with r squared times the cosine of 2 theta plus I times the sine of 2 theta. Okay, now let's say instead of just z squared, I wanted to find z cubed. Well, I know that z cubed is equal to z times z squared. So I'm going to take z, r cosine theta plus I sine theta, and I'm going to multiply that now by this complex number here, r squared times the cosine of 2 theta plus I times the sine of 2 theta. Now when I do this, I have to again multiply the moduli. So I have r times r squared, which is r cubed. Then I have to add the arguments. And if I add the arguments here, I end up with the cosine of 3 theta plus I times the sine of 3 theta. Okay, so maybe you've already seen the pattern here, but when we try to raise some complex number to a specific power, we need to raise the moduli to that power. So we raise the moduli to the power of 2 here because we're finding z squared. And then we multiply the argument by 2. So here we raised it to a third power because we're finding z cubed, and then we multiplied the argument by 3. And that's exactly what DeMoivre found. He actually proved this as well, so if we wanted to prove this, we'd have to prove it by induction, which we're not going to do. But he found this pattern and then was able to prove this pattern. Alright, so here's DeMoivre's theorem written up a little more formally. This is the book notation that you're going to see, and I'm just going to abbreviate this into our cis notation. So if we take some complex number z and we raise it to the nth power, and n is a natural number, this is r cis theta raised to the nth power. Okay, and we now know that we can just take the modulus and raise it to the nth power, and then multiply our argument by n. So we have r to the n cis n theta. So in other words, if you just read here, to take the nth power of a complex number, you're going to take the nth power of the modulus and multiply the argument also by n. Okay, here number 1, we're asked to find negative root 2 plus I root 2 raised to the 5th power. So this is currently a complex number written in rectangular form raised to the 5th power. Now prior to DeMoivre's theorem, which we are going to use on this problem, prior to that though, you could answer this problem using a binomial expansion and Pascal's triangle. So you could write out your coefficients, 1, 5, 10, 10, 5, 1. And then you could make your substitutions where a is equal to negative root 2 and b is equal to I root 2. So we would have 1 a to the 5th, b to the 0 plus 5 a to the 4th, b to the 1st, plus 10 a to the 3rd, b to the 2nd, and so on, right? And then we'd have to make those substitutions in here, and it would be a lot of tedious calculations. Instead, we're going to use DeMoivre's theorem, which shows us a much quicker way of computing this product. Now, in order to use DeMoivre's theorem, we have to write that complex number in cis form instead of rectangular form, so I'm going to find r and theta. So r is going to be found by taking the square root of negative root 2 squared, so 2, plus root 2 squared, another 2. So I'll get r is equal to 2. Now for theta, I know that the tangent of theta is equal to b over a, so root 2 over negative root 2, which is going to simplify and give me negative 1. So I have to think about where the tangent of theta will equal negative 1. Well, if theta is 3 pi over 4, or 7 pi over 4, we will get the tangent of theta equaling negative 1. Now, in order to pick the correct angle measure, I have to go back to this complex number here in that rectangular form and think about where that would be graphed. This is going to fall in quadrant 2. Okay, so because it falls in quadrant 2, I'm not going to pick 7 pi over 4. Theta must be 3 pi over 4. So now I have my cis notation. So I have r cis theta, which is 2 cis 3 pi over 4. Okay, now I want to raise this to the 5th power. So I'm taking this and raising it to the 5th power, so we know that all we have to do is raise our modulus to that power. So I have 2 to the 5th, And then I have to multiply that angle measure by 5. So I have 5 times 3 pi over 4. Now if I simplify, I have 32, then cis, this is going to be 15/4 pi. Okay, so now I'm supposed to put my answer in rectangular form. So I need to evaluate then 32 cis 15 pi over 4. I can write this in an equivalent angle measure. I can change that from 15 pi over 4 to its coterminal angle, which from 0 to 2 pi would be 7 pi over 4. Now the reason why these give me equivalent values for sine and cosine is because I would be rotating around the circle 1 full time. So that's 8 pi over 4. Okay, then I would go around 7 pi over 4 to get to 15 pi over 4. So those are coterminal angles. You don't have to do that. I just find it helpful to always rewrite it. All right, so I'm going to evaluate 32 cis 7 pi over 4. So that's 32 times the cosine of 7 pi over 4 plus I times the sine of 7 pi over 4. So I end up with 32. The cosine of 7 pi over 4 is going to be positive, so I have root 2 over 2. And then the sine of 7 pi over 4 is going to be negative, root 2 over 2. So I have 16 root 2 minus 16 root 2i. And that is this product here written in rectangular form. I think that's a lot faster. It might not have seemed faster since I was explaining it to you the first time, but that would be a lot less tedious calculations to do than Pascal's triangle. Now, in the key, I actually switched, I didn't realize this before I started working on this problem, that I wanted to switch this to make that a positive root 2 and this a negative I root 2 because it changed the angle. We've already used this angle, I think, in our previous lesson. So I just changed the angle a little bit. If you want to get practice at that, you can try doing positive root 2 minus I root 2 to the 5th power, and you can check your key to see if you got it correct. Okay, we'll move on now to number 2. All right, in number 2, we have to raise this complex number to the 10th power, and this would take forever if we were trying to use Pascal's triangle after trying to simplify it and expand all of that. It would take a long time. So we're going to convert this into cis notation first, and then we're going to apply DeMoivre's theorem. So if I want to write this in cis notation, I need to find r. So I'm going to take the square root of 1/2 squared, which is going to be 1/4, plus the square root of negative 1/2 squared, which is also 1/4. So I get the square root of 2/4, which will simplify to root 2 over 2. Okay, so that's my r value. Now for theta, I know that the tangent of theta is equal to b, negative 1/2, over a, 1/2. So I get tangent of theta equals negative 1. Now we know just from the previous problem that theta can either equal 3 pi over 4 or 7 pi over 4. And this time when we pick which angle to use, we note that this is going to actually lie in quadrant 4, so we're not going to pick 3 pi over 4, we'll use the 7 pi over 4. So in cis notation, I have r cis theta is equal to root 2 over 2, cis 7 pi over 4. Now we're trying to raise this complex number to the 10th power. Okay, so if we want to raise that to the 10th power, we know that all we have to do is raise our modulus to the 10th power. And then we have to multiply our argument by 10. So we have 7 pi over 4 times 10. Okay, now let's work on simplifying this. So I have root 2 to the 10th, which is like 2 to the 1/2 raised to the 10th power. So in that numerator, I'll get 2 to the 5th, and then over 2 to the 10th. Then cis of 7 pi over 4 times 10, that's going to reduce to, let's see, 70 pi over 4. So 35 pi over 2. All right, now we just work on evaluating a little bit further. 2 to the 5th over 2 to the 10th is the same as 1 over 2 to the 5th, or 1 over 32. And then cis of 35 pi over 2 is the same as cis of 3 pi over 2. Those are coterminal angles. So again, all you have to do is think about how many times you're going to go around one full circle, 2 pi units, and then whatever's left over will be your coterminal angle. Okay, so 3 pi over 2 and 35 pi over 2 give me the same exact cosine and sine values. And then I'll just evaluate. So I have 1/30 over 32 multiplied by the cosine of 3 pi over 2 plus I times the sine of 3 pi over 2. And evaluating here, the cosine of 3 pi over 2 is 0, and the sine of 3 pi over 2 is negative 1. So I end up with, let's see if I distribute, negative 1 over 32i. So this is that complex number here written in rectangular form, which is what the directions asked, but this is the product when I try to multiply 1/2 minus 1/2 to the I by itself 10 times. All right, now in the next portion of the lesson, we're going to be finding nth roots of complex numbers. So we actually apply DeMoivre's theorem to finding an nth root, and I think this is a lot trickier than just using DeMoivre's theorem. Here we're applying it. We're actually working kind of backwards. So we say that z is an nth root of w if for some natural number n, we have z to the n is equal to w. Okay, so in other words, let's say n was equal to 3. Then we'd have z cubed is equal to w. We would call z a cube root then of w. So we're finding nth roots, meaning we could be solving z to the 8th is equal to w. So that would be an 8th root. Okay. Now, in order to solve for the nth roots of complex numbers, we need to use DeMoivre's theorem, and we're going to work backwards. But one of the things that we're going to rely on is the fact that when you express a complex number in its polar form, so for example, r cosine theta plus I sine theta, this is not unique because I can always add to theta 2 pi, right? 2 pi n would represent an infinite number of angle values that would be the exact same, values for cosine and sine because those are periodic functions. The period is 2 pi. So I can continue to add 2 pi to that angle as many times as I want to get another complex number that is exactly the same as my original, okay? All right, in number 3, we're asked to find all complex cube roots of 27i, which means we want to find all z of the form z cubed is equal to 27i. In order to apply DeMoivre's theorem here, I have to be able to rewrite both sides of this equation in polar form. So I'm going to rewrite z, this is some complex number, as r cis theta cubed. Okay, so that represents z cubed. Now on the right-hand side, this is right now a complex number, but it's written in rectangular form, so I have to work on changing that from rectangular form to polar form. Now 27i in rectangular form is equivalent to 0 plus 27i. So I just wanted to show you that so you can see the a and the b clearly. Now we need to find, for 27i, we need to find its polar form, which means we need to have a modulus and we need to have an angle measure. But I don't want to call it r and theta because I think you might get it confused with this r and this theta. These are not equivalent to each other. Okay, so we're just right now trying to convert the right-hand side into polar form. So if I find r sub 0, let's call it r sub 0 right now, I need to take the square root of 0 squared plus 27 squared, which will give me 27. So there's the modulus. Now when I calculate theta, I'm setting up the tangent of theta is equal to 27b over a, which is 0. So this is undefined. Now there's only 2 spots where the tangent of theta is undefined, and that's going to be at 3 pi over 2 and at pi over 2. But in this case, I need to go back and think about where 27i would be plotted in the complex plane. 27i is up here, which means we are not going to select 3 pi over 2. We want to take pi over 2. So in cis form, 27i is represented as 27 cis pi over 2. Okay, now that both sides are written in polar form, we can actually see how DeMoivre's theorem has already been applied. If we take r cis theta and cube it, we end up with this product 27 cis pi over 2. Our goal is to undo DeMoivre's theorem so that we find the original complex number that gives us 27 cis pi over 2. So we're solving this equation. Now, what is helpful here is to simplify this left-hand side. We have r cubed, since if I'm raising this complex number to the 3rd power, I need to cube that modulus. And then I have to multiply the argument by 3. So I have r cubed cis 3 theta is equal to 27 cis pi over 2. All right, now based off of this equation, I can see that r cubed must equal 27, which means I can find my r value by just taking the cube root of 27. So r must equal 3. I also can see that 3 theta must equal pi over 2. But you got to remember that this is not the only way to represent 27i in polar form. Remember, there's an infinite number of ways to represent any complex number in polar form because you can always add 2 pi n to pi over 2. So any multiple of 2 pi n can be added to pi over 2, and you're going to get another angle measure which has the exact same sine and cosine values. So I'm going to rely on that, and this is really similar to what we did when we were solving trig equations. If we want to solve for theta, we have to divide by 3, and we're going to divide by 3 everywhere here. So we end up with pi over 6 plus 2/3 pi n. Okay, now that we have r and theta, I can write out each of my distinct complex cube roots here. So one of those complex cube roots I'm going to denote as z sub 1. So I should have z sub 1, z sub 2, and z sub 3 since I'm solving for 3 complex cube roots. So if it was, finding the 5th roots, you would have z1 through z5. So anyhow, let's work on z sub 1. Well, I need to write this as r cis theta. So I have r, which is 3, cis, my theta value. The first one I'm just going to use is pi over 6. Okay, I'm not going to add a multiple of 2/3 pi n yet. Now, for my second complex cube root, I can take 3 cis pi over 6 plus a multiple of 2 pi over 3. I'm going to use the first multiple. So I'm going to add that, and if I simplify, I have 3 cis 5 pi over 6. Now for z sub 3, so my third complex cube root, I'll take that same r value, 3 cis pi over 6 plus, now I'm going to multiply 2 times 2/3 pi. So I'm going to add 4/3 pi in, or 4/3 pi, sorry. All right, here I end up with 3 cis, let's see, this is 9/6 pi, which will simplify to 3/2 pi. So 3 cis, 3/2 pi. Okay, now what this is saying is that you have 3 distinct cube roots. Essentially, if you were to take this in cis form, that complex number, and you were to cube it, you will end up with 27i. So each of these produce, after you cube them, the same exact complex number, 27i, okay? So that's our goal. We wanted to find what originally had been cubed in order to get 27i. So that's what we've done. Now we want to convert this back to rectangular form. So I'm going to pause the video and we're going to work on that so I can get a little bit more room here. Okay, for z sub 1, our first complex cube root, I want to take 3 and multiply that by the cosine of pi over 6, which is going to be root 3 over 2, plus I times the sine of pi over 6, which is 1/2. So to simplify here, I get 3 root 3 over 2 plus 3/2 I. So this is that first complex cube root now written back in rectangular form. For z sub 2, I need to take 3 and multiply that by the cosine of 5 pi over 6, which is going to be negative root 3 over 2, plus I times the sine of 5 pi over 6, which is still 1/2. So we end up with negative 3 root 3 over 2 plus 3/2 I. Then for z sub 3, we'll take 3 and multiply that by the cosine of 3 pi over 2, which is 0, plus I times the sine of 3 pi over 2, which is negative 1. And after I distribute here, I end up with 3i times negative 1, so negative 3i. All right, so those are your 3 distinct complex cube roots of 27i. So each of these solves the equation z cubed is equal to 27i, okay? So I just want to review real quick what we're doing in this problem so that we can go to the next 2, which are each different than the one before. So in example 3 here, we started by trying to rewrite an equation that represented what we're asking. We want to find complex cube roots of 27i. Then we broke it down. We wrote each side of this equation in polar form, okay? Then I just simplified that left-hand side here to show, after using DeMoivre's theorem, what you would get. You would get r cubed cis 3 theta, because we know we multiply the argument by 3, and we also raise the modulus to the 3rd power. Then after that, we set each part equal to each other. So r cubed must equal 27, 3 theta must equal pi over 2. So then when we got our theta values, we realized that it's not just pi over 6, there's actually a couple more values of theta that will give us the exact same cosine and sine values here. So that's how we ended up adding 2/3 pi to multiples of that to find z1, z2, and z3. Okay, so we found those 3 distinct complex cube roots, wrote them in rectangular form, and we solved our equation. All right, in number 4, we're asked to find the 4th roots of negative 16. So I'm solving z to the 4th is equal to negative 16. Remember, we want to write both sides here in polar form. So we're going to express this complex number z as r cis theta raised to the 4th power. Then on the right-hand side, we need to rewrite negative 16 in terms of its cis notation. So let's find r sub 0 and theta sub 0. So r sub 0 is going to be found by taking the square root of negative 16 squared, so it'll end up being positive, plus 0 squared. So we end up with 16, okay, because this is really negative 16 plus 0i. Okay, now for theta, we know the tangent of theta sub 0 is going to be b over a, so 0 over negative 16. So we want to know where the tangent of theta is equal to 0. So theta must be either 0 or pi, okay, because that's where the tangent of theta is equal to 0. Now in this case, go back to negative 16 and think about where that would be plotted in the complex plane. That's going to be over here, which means we're not going to use 0, we're going to use pi. So we have negative 16, which can be rewritten as 16 cis pi. All right, now let's work on simplifying the left-hand side. When we take r cis theta and raise it to the 4th power, we raise the modulus to that power, and we multiply the argument by 4. So we have r to the 4th cis 4 theta is equal to 16 cis pi, which means r to the 4th is equal to 16, so we can see r is 2. We also see that 4 theta is equal to pi, and again, remember that this is not a unique angle measure. You can add 2 pi n, okay? So if we divide now by 4, we end up with theta equaling pi over 4 plus pi over 2 n. All right, now let's write out each of our complex 4th roots here. We have z sub 1, z sub 2, z sub 3, and a z sub 4. So those are our 4 complex 4th roots. So z sub 1 will be found by taking 2 cis pi over 4. For z sub 2, we need to take 2 cis, and then we're going to take pi over 4 and add a multiple of pi over 2. And we can simplify that as 2 cis 3 pi over 4. Now for z sub 3, we need to take 2 cis pi over 4, but this time we're going to add 2 multiples of pi over 2, so 2 times pi over 2. So really we're just adding pi here, so we get 2 cis 5 pi over 4. Okay, so you can see that you can just add pi over 2 to each of these arguments to get your new argument. That would be fine as well. So in the last one, if I just add pi over 2 to 5 pi over 4, I end up with 2 cis 7 pi over 4. Now sometimes they do ask you to do it in degrees, so make sure you're comfortable evaluating in degrees as well. But now we want to put this in rectangular form, so let's evaluate. All right, if I want to write our first complex fourth root here, z sub 1, in terms of its rectangular form, I need to make sure I multiply 2 by the cosine of pi over 4, which is root 2 over 2, plus I times the sine of pi over 4, which is also root 2 over 2. So I end up, after I simplify here, with root 2 plus root 2i. So this is the rectangular form for that complex fourth root. Now I will let you guys evaluate z2, z3, and z4. Just make sure that you're comfortable with leaving something in polar or trig form. So this is in polar form here with the cis notation. And that you can also evaluate and get it back to its rectangular form. You might also be asked to leave it in degrees as well. So you'll leave, instead of pi over 4, you would use 45 degrees. But that's about it. And then we'll move on to the next problem. All right, in problem 5, we want to find the fourth roots of 2 plus 2 root 3i. So I want to solve z to the fourth is equal to 2 plus 2 root 3i. Now I'm going to change each of these sides into polar form. So I have r cis theta raised to the fourth power is equal to, in this case, r will be the square root of 2 squared, which is 4, plus 2 root 3 squared. So that'll give me 4 times 3, 12. So if I add those and I take the square root, I end up with 4. So r is 4, and then for theta, we need to take the tangent of 2 root 3 over 2. So we need to think about where the tangent of theta is equal to root 3. So theta can either be pi over 3 or 4 pi over 3. And actually, I should be using theta sub 0 and r sub 0. Sorry about that. In this case, since 2 plus 2 root 3i is going to be found in the first quadrant, I don't want to use 4 pi over 3. So I'll use theta sub 0 as pi over 3. So if I want to rewrite 2 plus 2 root 3i in polar form, I write that as 4 cis pi over 3. All right, now I'm going to simplify that left-hand side. If I use DeMoivre's theorem, that tells me that I raise the modulus to the fourth power, so r to the fourth cis, and then I multiply that argument by 4. So I have r to the fourth cis 4 theta is equal to 4 cis pi over 3. So r to the fourth is equal to 4, which means r is equal to root 2. We also see that 4 theta will equal pi over 3, but when you set this one up, remember that you're going to add 2 pi n, since this is not the only way to represent 2 plus 2 root 3i in terms of its polar form. There's an infinite number of ways, so that's why we attach 2 pi n to that. So we'll solve for theta. We end up with pi over 12 plus pi over 2n. So we're just going to divide everything here by 4, okay? All right, now if we want to list our fourth roots here, we have z sub 1, z sub 2, z sub 3, and z sub 4. So z sub 1 is going to be root 2, that's my r value, times cis of pi over 12. Now z sub 2 will be root 2 cis pi over 12 plus pi over 2. So what is that? 6 twelfths pi. So we have 7 twelfths pi here after we simplify. And then z sub 3 will be root 2 cis, and then I'm just going to take that previous value and add another pi over 2. So I would end up with 13 twelfths pi here. And then z sub 4, that fourth complex root will be root 2 cis. Again, take 13 twelfths pi and add another 6 pi over 12. So you get 19 twelfths pi. Okay, these are not values that are very easy for us to calculate because we don't have these memorized on our unit circle. So I'm just going to leave it here. If you needed to use a calculator, though, you should be able to evaluate that correctly using your calculator, and then you would leave your answer as rectangular form in terms of, a real number here, and then so it'll have a decimal probably. plus a real number with I. Okay, that would be in its rectangular form. So you are allowed to use a calculator just to do some of the bookwork problems, but you won't use one on the quiz. So make sure you do know how to evaluate, but obviously we will not ask you to evaluate something like 7/12 pi because it'd be a lot more complex for us. All right, there's just one more thing I wanted to mention. We just found 4 fourth roots. Okay, so in other words, if we were to take each of these complex numbers written in polar form and we were to raise it to the 4th power, we will end up with 2 plus 2 root 3i. So those are the solutions essentially to the equation z to the 4th is equal to 2 plus 2 root 3i. Okay? All right, that is the end of the lesson. I know those are some long problems that take a little bit more time and a lot more thinking, but as long as you understand the process, I think it'll be pretty easy for you. So make sure that tomorrow you get a lot of practice and you ask a lot of questions. So nice job. See you guys in class tomorrow.